Now, in this lecture, we will find out the radius of the small circle. In the drawing, we have a small circle that is described by a semicircle. We know that side DB equals to 4 units, side CD equals to 3 units, angle CDB equals to 90 degrees. And we want to find out the radius of this small circle that is inside the semicircle. Okay, so first of all, we'll do a construction. We will complete the semicircle to a circle. So we completed the semicircle to a circle. In the next step, we will extend line segment CD by a straight line until it touches the circle. And we will define the touching point of the extended line segment CD and the circle as point E. And actually, we created here a second semicircle that is a mirror image of the original semicircle. This semicircle is the mirror image of this original semicircle, and here we extended the straight line CD by a straight line, and when you extend the straight line by a straight line, the result must be a straight line. So by extending the straight line CD by a straight line, we created line segment CE, so the result CE must be also a straight line. So we can write down that line segment CE is a straight line. And we have the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So if we focus on this side of the straight line CE at point D, then the sum of the angles must be equal to 180 degrees. So at point D, so which angles we have at this side of the straight line C at point D, we have here 90 degrees. And we have also this angle EDB. In total, the sum of those two angles must be equal to 180 degrees. According to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So here we subtract, so we have 90 degrees plus angle EDB must be equal to 180 degrees. We subtract 90 degrees from this equation, and we get that angle EDB equals to 180 degrees minus 90 degrees, it is 90 degrees. So we found out that this angle EDB equals to 90 degrees, it is a right angle. So here angle CDB equals to 90 degrees and angle EDB also equals to 90 degrees. Actually, line segment CD and line segment ED, here line segment ED is the mirror image of line segment CD. Again, the line segment DE that we created is a mirror image of line segment CD. Why? Because angle CDB equals to 90 degrees and angle EDB also equals to 90 degrees. Therefore, line segment ED is the mirror image of line segment CD. And therefore, we can write down that CD equals to ED. CD equals to ED by symmetry. Okay? When you look at yourself in the mirror, you see yourself exactly in the same dimension as you are in reality, but in the opposite direction. And the same thing is true here, that ED is the mirror image of CD, but in the opposite direction. Therefore, CD equals to DE, because ED is the mirror image of CD. Okay? So CD equals to 3 units according to what is given us in the question. CD equals to 3 units. So from this equation, ED equals to CD equals to 3 units. We will conclude that ED is also equals to 3 units. ED equals to 3 units. So here ED equals to 3 units. Okay. In the next step, I will present to you a new rule that is actually rule number 1. According to rule number 1, if chord AB intersects with chord CB, intersects with chord CD, at point O. Point O is the intersection point of chord AB with chord CD. Then AO times OB equals to CO times OD. Okay? So we have chord AB this is chord AB that intersects with chord CD. This is chord CD. So I repeat again, chord AB intersects with chord CD at point O. Point O is the intersection point of chord AB with chord CD. Therefore, according to rule number 1, AO times OB equals to CO times OD. AO times OB equals to CO times OD. Okay, so we can implement rule number 1 in our drawing, because in our drawing we have here chord AB, this is chord AB, that intersects with chord CE at point D. So I write it down. Now drawing, we have chord AB intersects with chord CE at point D. I'll repeat again, chord AB intersects with chord CE at point D. Point D is the intersection point. Point D is the intersection point of chord AB with chord CE. Therefore, according to rule number 1, we will get that AD times DB will be equal to CD times DE. I repeat again, according to rule number 1, we get that AD times DB equals to CD times DE. Okay? ED is the missing line segment, therefore we leave it as it is. DB equals to 4 units according to what is given us the question, so we will substitute DB by 4, and it is equal to CD. CD equals to 3 units according to what is given us the question. And we already found out that DE is 3 units, so it is CD times DE, and DE is 3 units. So in conclusion, found out that according to equation number 1, AD times 4 equals to 3 times 3. Okay? 3 times 3 is 9. So I write it down. We get that 4 times AD equals to 9. Here we will divide this equation by 4, and we'll get that AD equals to 9 over 4. So if I know that AD equals to 9 over 4, we can write here that AD equals to 9 over 4 units. We know that the diameter of the big circle is AB. AB is also the diameter of the two semicircles. And the diameter of any circle is twice as long as the radius. So actually, the radius, we define the radius of the big circle as capital R. So capital R will be equal to the diameter that is AB over 2. Okay? AB equals to AD plus DB. AB equals to AD plus DB. And all divided by 2, of course. AD equals to 9 over 4. We substitute AD by 9 over 4. And DB equals to 4 units according to what is given us the question. All divided by 2. So here we have 9 over 4 plus 4. So we'll multiply 4 by 4 and then we'll divide it by 4 in order to have a common factor with 9 over 4. And we'll get that 9 plus 9 times 9 plus 4 times 4 is 16 over 4 divided by 2. 9 plus 16 is 25. Over 4 over 2. We'll move 2 to the denominator and we get that 25 over 4 times 2. It is equal to the radius of the big circle. Here is 25. 4 times 2 is 8. So in conclusion, we found out that the radius of the big circle, that is also the radius of the semicircle, is equal to 25 over 8 units. Okay? So, in the next step, we will define the center of the big circle as point P. We will define the center of the small circle as point Q. And we will find out the length of the short line segment DP. What is the length of the short line segment DP? From the drawing, it is very easy to see that the length of the short line segment DP is equal to DB minus PB. And repeat again. The length of the short line segment DP, it is equal to DB minus PB. DB equals to 4 units according to what is given as the question. So we'll substitute DB by 4. Minus PB. P is the center of the big circle. B is the point of the big circle itself. This is exactly the definition of a radius. That is to say, PB equals to the radius of the big circle, that is to say it is equal to capital R. So in conclusion, we found out that dP equals to 4 minus capital R, but we have already found out that capital R equals to 25 over 8, so we will substitute capital R by 25 over 8. So dP equals to 4 minus 25 over 8. So here we will multiply 4 by 8 and then we will divide it by 8 in order to have a common factor with 25 over 8. And we get that dP is actually equals to 4 times 8 is 32 minus 25 over 8. 32 over 25 is 7. In the denominator we have 8. So in conclusion, we found out that the short line segment dP, it is equal to 7/8 units in its length. So we can write here that dP equals to 7/8. Okay. In the next step we will define the point of tendency of tangent dB with this small circle as point M. I repeat again, point M is the point of tendency of tangent dB with this small circle. And we'll also define the point of tendency of tangent CD with this small circle as point O. We'll join together points Q and O by a straight line. I'll repeat again that point O is the point of tendency of tangent CD with this small circle. What is the definition of line segment QO? Q is the center of the small circle. O is the point on the small circle itself. Therefore, QO is the radius of the small circle. We define the radius of the small circle as small r. So QO equals to small r. It is the radius of the small circle. So here we have the radius QO. It is drawn to the point of tendency. That is to say, it is drawn to point O. That is the point of tendency of tangent CD with this circle. And whenever we have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. Here, tangent CD will be perpendicular to the radius OQ. So if CD is perpendicular to OQ, it means that this angle equals to 90 degrees and this angle will be also equal to 90 degrees. Okay, likewise, we join points M and Q together by a straight line. Point M is the point of tendency of tangent dB with this small circle. What is the definition of QM? Q is the center of the small circle. M is a point on the small circle itself. Therefore, QM is the radius of the small circle that is equal to small r. So here the radius QM, it is drawn to the point of tendency. That is to say, the radius QM is drawn to point M, that is the point of tendency of tangent dB with this small circle. Okay, and whenever you have a radius that is known to the point of tendency, then the tangent dB will be perpendicular to the radius MQ. I will repeat again. Tangent dB will be perpendicular to the radius MQ. So if dB is perpendicular to MQ, it means that this angle equals to 90 degrees and this angle will be also equal to 90 degrees. Okay, so actually if we focus on quadrilateral OQDM, in quadrilateral OQDM we have 1, 2, 3 right angles. So in quadrilateral OQDM, this quadrilateral we have 1, 2, 3 right angles. And the sum of 3 right angles is 90 times 3 is 270 degrees. Plus the size of the fourth angle, that is actually angle OQM. In total, the sum of those 4 angles, they must be equal in total to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Okay? Here we'll subtract 270 degrees from this equation, and we'll get that the missing angle OQM, is equal to 360 degrees minus 270 degrees, it is 90 degrees. So this angle OQM equals to 90 degrees, it is a right angle. Therefore, in quadrilateral OQDM, we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle, so we will relate to quadrilateral OQDM as a rectangle. Quadrilateral OQDM is a rectangle because of the fact that it has 4 right angles. Okay, quadrilateral OQDM is a rectangle. But we know that the opposite sides of a rectangle are equal to each other. So the opposite sides of rectangle OQDM are equal to each other. That is to say OQ equals to DM. OQ equals to DM. According to the rule that the opposite sides of a rectangle are equal to each other, we get that in rectangle OQDM, OQ equals to DM. But we have already found out that OQ equals to small r, that is the radius of the small circle. So we can write here that OQ equals to small r, and from this equation r equals to OQ equals to dm, we will derive that dm is also equals to small r. Okay, dm is also equals to small r, so we can write here that dm equals to small r. Okay. And what is the length of line segment PM? The length of line segment PM, for the drawing it is very easy to see that the length of line segment PM, it is equal to dm minus dp. dm minus dp. I'll repeat again. PM equals to dm minus dp. So PM equals to dm equals to small r, according to what we just found out. We'll substitute dm by small r minus dp. We already found out that dp equals to 7/8. So in conclusion, we found out that PM equals to small r minus 7/8. So we can write here that PM equals to small r minus 7/8. Okay. Here, this point is the point of tendency of the large point of the small circle with the big circle. The big circle is located inside, the small circle is located inside the big circle, and therefore this is the internal large point. Okay, this is the, we define this point as point S, and point S is the large point of the big circle with the small circle, but because of the fact that the small circle is inside the big circle, it is defined as internal large point. So in the next step, I will present to you a new rule that is actually rule number 2. According to rule number 2, if two circles have an internal length between them, in this case, as I already said, those two circles, the big circle and the small circle, have an internal length between them. Why? Because they are touching each other internally at point S. So, according to rule number 2, if two circles have an internal length between them, then the straight line that connects their centers passes through the launch point. So I will read rule number 2 again. According to rule number 2, if two circles have an internal length between them, then the straight line that connects the centers, then the straight line that connects their centers passes through the lunge point. So here we have those two circles have an internal between them at point S, that is to say they are touching each other internally at point S. Point S is the lunge point. And according to rule number 2, the straight line that connects their centers together is PQ. Why? Because P is the center of the big circle and Q is the center of the small circle. PQ is the straight line that connects their centers together. And according to rule number 2, that this straight line PQ passes through the lunge point, that is to say, the straight line PQ passes through point S, that is the lunge point of the two circles. So here we have the straight line PQ that connects the two centers together, and according to rule number 2, the straight line PQ, the straight line passes from point S, that is the lunge point of those two circles. Okay, I'll repeat again that the straight line that connects their centers together is PQ, and this straight line PQ passes from point S. So we can derive from it that points P, Q, and S are located on the same straight line. According to rule number 2, points P, Q, and S are located on the same straight line. Okay, points P, Q, and S are located on the same straight line, or you can also say that line segment PQS is a straight line. Okay, line segment PQS, the red line is a straight line. Okay, and what is the length of line segment QS? Q is the center of the small circle. S is a point on the small circle itself. This is exactly the definition of a radius. That is to say, QS is the radius of the small circle that is equal to small r. Okay, QS equals to small r. And what is the definition of line segment PS? PS. P is the center of the big circle. S is a point on the big circle itself. This is exactly the definition of a radius. That is to say, PS equals to capital R. That is actually the radius of the big circle. So PS is the radius of the big circle, but we have already found out that capital R equals to 25/8. In conclusion, we found out that PS equals to capital R equals to 25/8. And what is the length of line segment PQ? Here, the length of the line segment PQ from the drawing, it is very easy to see that PQ equals to PS minus QS. Again, PS minus QS equals to PQ. PQ equals to PS minus QS. But we've already found out that PS equals to capital R. So we substitute PS by capital R, that is actually the radius of the big circle, minus QS. We already found out that QS equals to small r, it is the radius of the small circle. So in conclusion, we found out that PQ equals to capital R minus small r. But we have already found out that PQ equals to 25, capital R equals to 25 over 8. So we can substitute capital R by 25 over 8, and we get that PQ in conclusion, PQ equals to 25 over 8 minus small r. Okay? So we can write here that PQ equals to 25 over 8 minus small r. In the next step, we will implement the Pythagoras theorem on the green right triangle QPM. So I will copy the right triangle QPM in a new page, and we will implement the Pythagoras theorem on this right triangle QPM. Okay? So this is the right triangle QPM that I copied from the original drawing. We have already found out that QP equals to 25 over 8 minus R. We have already found out that PM equals to small r minus 7/8. And we've already found out that QM equals to small r, it is the radius of the small circle. So this is the right triangle QPM, and we will implement the Pythagoras theorem here by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, we get that the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is QP, therefore the square of the hypotenuse is QP squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to QM squared plus PM squared. Okay? QP equals to 25 over 8 minus R. So QP squared will be equal to 25 over 8 minus R squared. QM equals to small r, so QM squared will be equal to small r square plus pm square. Pm equals to r minus 7/8. Therefore, pm square will be equal to r minus 7/8 square. Okay. So here we will open the brackets on both sides of this equation number 1, and we get that according to equation number 1, 25/8 minus r squared. We'll find the value of this expression according to the algebraic identity that a minus b squared equals to a squared plus b squared minus 2 times ab. Therefore, 25/8 minus r squared will be equal to 25 square over 8 squared, that is 625/64 plus r squared minus 2 times 25/8 times r. And it is equal to r squared, r minus 7/8 squared it is equal to r squared plus 7/8 squared is 7 squared, that is 49, over 8 squared, that is 64, minus 2 times r times 7/8. So here we have r squared on both sides of the equation number 1, so r squared will get cancelled. And here we have 2 times 25 minus 2 times 25 r over 8. We will divide both the numerator and the denominator of this expression by 2, and we will get that minus 2 over 2 is minus 1, so minus 2 will get cancelled, and we left only in the numerator with minus 25 r over 8 is divided by 2, so it is 4. So in conclusion, this expression equals in total to minus 25 r over 4. And we have also here 625/64. This is question number 1. And it is equal to r squared plus 49/64. So here we have the expression of minus 2r times 7/8. We will divide both the numerator and the denominator by 2. So minus 2 over 2 is minus 1, so minus 2 will get cancelled. In the numerator we left only with minus 7r. In the denominator we have 8. We have to divide 8 by 2, so it is 4, 8 over 2 is 4. So in conclusion, this expression, minus 2r times 7/8 equals to minus 7r over 4. So here we will multiply this equation number 1 by 64. And we get that according to equation number 1, (625) times 64 over 64 is 625. We have to multiply this expression by 64, so it is actually equals to minus 64 over 4 is minus 16. And in the numerator we have 25r over. So in conclusion, this expression minus 25r over 4 after we multiply it by 64, it is equal to minus 16 times 25r, and it is equal to r squared. R squared times 64 is 64r squared. Forty-nine times 64 over 64 is 49. And here we have minus 64 over 4 is minus 16. So this expression in total will be equal to minus 16 times 7r. Okay. So in conclusion, we found this, and according to question number 1, 625 minus 16 times 25r is minus 400r, and it is equal to 64r squared plus 49, and minus 16 times 7r is minus 112r. Okay, so here we will add 400r to this equation number 1, and we get that according to equation number 1, 625 400r minus 400r is 0, so we left in this side of equation number 1 only with 625. That is equal to 64r squared plus 49, and we have here 400r minus 112r, it is plus 288r. Okay, so here we will subtract 625 from this equation number 1, and we will get that 625 minus 625 is 0. In the other side of equation number 1 we have 64r squared plus 288r. 49 minus 625 is minus 576. So here we will divide this equation by 32, and we will get that according to equation number 1, 64 over 32 is 2, so in total this expression equals to 2r squared plus 288r over 32 is 9r minus 576 over 32 is minus 18, and 0 over 32 is 0. So in conclusion, we got the quadratic equation that 2r squared plus 9r minus 18 equals to 0. In this quadratic equation, the coefficient A equals to 2, the coefficient B equals to 9, and the coefficient C equals to minus 18. And the variable that we are looking for in this quadratic equation is R, so X equals to R. And the general formula to solve a quadratic equation, for solving out the quadratic equation, is X equals to minus B plus minus square root of B squared minus 4 times A times C over 2A. A, B, and C, this quadratic equation of the coefficients of the quadratic equation, and X is the variable that we are looking for. In our specific quadratic equation, the variable that we are looking for is R, so we substitute X by R. So here we put the data inside this equation, and we find out that X that is equal to R equals to minus B, B equals to 9, so minus B is minus 9, plus minus square root of B squared. B equals to 9, so B squared is 9 squared, that is 81, minus 4 times A is 2, so it is minus 4 times 2, times C is minus 18, divided by 2A. A is 2, so 2 times 2 is 4. So here we found out that R equals to minus 9 plus minus 4 times 2 is minus 8, and minus 8 times minus 18 is plus 144. So inside the root we have left with 81 plus 144 divided by 4. So here R equals to, R is the radius of the small circle, that is equals to minus 9 plus minus 81 plus 144 is 225. So inside the root we left only with 225 over 4. So actually we get here that R, the radius of the small circle, equals to minus 9 plus minus square root of 225 is 15 over 4. So here we have two solutions that are possible for R. The first solution for R is that R equals to minus 9 minus 15 over 4. Minus 9 minus 15 is minus 24, and minus 24 over 4 is minus 6. So R equals to minus 6. That is a negative number. But here R is the radius of the small circle. R is the length of the radius of the small circle. And R is a length, it must be a positive number. Write it down. R is the length of the radius of the small circle. And as a length, it must be a positive number. Therefore, it can never be equal to minus 6, that is a negative number. We will cancel the solution and we left only with the second solution, that R equals to minus 9 plus 15 over 4. Minus 9 plus 15 is 6, and 6 over 4. R equals to 6 over 4. We divide both the numerator and the denominator of 6 over 4 by 2. 6 over 2 is 3 and 4 over 2 is 2. So in conclusion, we found out that R, the radius of the small circle, it is equal to 3 halves units, or in terms of numbers, it is equal to 1.5 units. Okay. I'll repeat again. The radius of this small circle is equal to either 3 halves units, or in terms of numbers, it is equal to 1.5 units. In the next step, I will summarize the lecture. Actually, we wanted to find out the radius of this small circle, and we know that line segment CD equals to 3 units, line segment DB equals to 4 units, and then again CDB equals to 90 degrees. So in the first step, we did the construction, we completed the semicircle to a circle. As I already told you, the second semicircle that we created is the mirror image of the original semicircle. And then we extended the straight line CD by a straight line until it touches the circle at point E. And here, when you extend the straight line by a straight line, the result must be a straight line. Therefore, when we extended the straight line CD by a straight line, we got line segment CE, that it is also must be a straight line. So here we can write down that CE is a straight line. This line segment CE is a straight line, and we have the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So if we focus on this side of the straight line CE at point D, at this point D, then the sum of the angles must be equal to 180 degrees. So which angles we have at this side of C at point D? We have here 90 degrees, and then get EDB. So at point D, we have 90 degrees plus angle EDB. In total, they must be equal to 180 degrees, according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. Here, we subtracted 90 degrees from this equation and found out that the missing angle EDB equals to 90 degrees. So this angle EDB equals to 90 degrees, it is a right angle. Okay, so we know that angle CDB equals to 90 degrees and angle EDB also equals to 90 degrees. And when we extended the straight line CD by straight line, we got the straight line DE. And because of the fact that both those two angles, they are equal to each other, they are equal to 90 degrees, it means that DE, line segment DE, is the mirror image of line segment CD. Okay? Line segment DE, this line segment, is the mirror image of line segment CD. And because of the fact that line segment DE is the mirror image of CD, it means that the length of the mirror image is always equal to the length of the image itself. So here, the length of the mirror image, that is actually DE or ED, must be equal to the length of the image itself, which is CD. Okay, so CD equals to DE by symmetry. When you look at yourself in a mirror, you see yourself exactly as you are, exactly with the dimensions that you are in the reality, but in the opposite direction. The same thing is true to those two line segments. Because DE is the mirror image of CD, it means that DE equals to CD, but in the opposite direction. Okay? So, in conclusion, CD equals to DE, but we know that CD equals to 3 units. It's given us that CD equals to 3 units, so we can write here that CD equals to 3 units, and from this equation 3 equals to CD equals to DE, we will derive that DE or ED is also equals to 3 units. Here DE also equals to 3 units. Then I presented to you rule number 1. According to rule number 1, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. So we have chord AB, this is chord AB, that intersects with chord CD at point O. Point O is the intersection point of chord AB with chord CD. Okay? So if this is the data that has been given to us, then according to rule number 1, we will get that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. AO times OB equals to CO times OD. We can implement rule number 1 in our drawing. Why? Because in our drawing we have chord AB that intersects with chord CE at point D. Okay, here chord AB intersects with chord CE at point D. Point D is the intersection point of chord AB with chord CE. Therefore, according to rule number 1, we will get that AD times DB equals to CD times DE. Again, AD times DB equals to CD times DE. I'll repeat again, AD times DB equals to CD times DE. Okay, so AD is the missing line segment. We'll leave it as it is. DB equals to 4 units according to what is given as the question. CD equals to 3 units according to what is given as the question. And we have already found out that D equals to 3 units. So in conclusion, I found out that 4 times AD equals to 3 times 3. 3 times 3 is 9. So in conclusion, I found out that 4 times AD equals to 9. We divide this equation by 4 and we get that AD equals to 9 over 4 units. So this is the missing line segment AD equals to 9 over 4 units. Okay. We know that in the drawing AB is the diameter of this big circle and also the diameter of the semicircles. And any diameter is twice as long as the radius. So if we divide the diameter by 2, we'll get the radius. So we define the radius of the big circle as capital R. So capital R equals to the diameter that is AB over 2. Okay? Here we know that AB equals to AD plus DB. So we substitute AB by AD plus DB, all divided by 2. AD equals to 9 over 4 units. DB equals to 4 units according to what is given us in the question, all divided by 2. Here we'll multiply 4 by 4 and then we divide it by 4 in order to become a factor with 9 over 4. So, and 9 plus 4 times 4 is 16 over 4 over 2. 9 plus 16 is 25. 25 over 4 over 2. We remove the 2 to the denominator. We get the 25 over 4 over 2. It is actually 4 times 2. 4 times 2 is 8. So in conclusion, we found out that the radius of the big circle that is defined as capital R equals to 25 over 8 units. Okay. Then we define the center of the big circle as point P and the center of the small circle as point Q. What is the length of line segment DP? Yeah. From the drawing, it is very easy to see that the length of this line segment DP, it is equal to dB minus PB. dB minus PB equals to dP. dP equals to dB minus PB. Okay, dB equals to 4 units according to what is given us the question. What is the length of PB? P is the center of the big circle, B is the point of the big circle itself. This is exactly the definition of a radius. So PB is the radius of the big circle that is equal to capital R. So we substitute PB by capital R and we get that dP equals to 4 minus capital R. But we already found out that capital R equals to 25 over 8. Here, capital R equals to 25 over 8, so we substitute capital R by 25 over 8, and we get that dP equals to 4 minus 25 over 8. Here we multiply 4 by 8 and then we divide it by 8 in order to overcome a factor with 25 over 8. 4 times 8 is 32. 32 minus 25 over 8. This is the value of dP. 32 minus 25 is 7. So it is 7 over 8. So in conclusion, we found out that dP equals to 7/8. So I can write here that dP equals to 7/8. Okay. In the next step, we defined the point of tangency of tangent dB with this small circle as point M. This is the point of tangency of tangent dB with this small circle. We define this point M, and we define the point of tangency of tangent CD with this small circle as point O. Point O is the point of tangency of tangent CD with this small circle. Then from point Q we draw the radius to point O. QO is the radius of the small circle because of the fact that point Q is the center of the small circle and point O is the point on the small circle itself. This is exactly the definition of a radius. So QO equals to small r, that is the radius of the small circle. Here we have the radius QO that is drawn to the point of tendency. That is to say, it is drawn to point O, that is the point of tendency CD and this circle. And whenever you have a radius that is drawn to the point of tendency, then the tangent CD will be perpendicular to the radius OQ. So if CD is perpendicular to OQ, it means that this angle equals to 90 degrees and this angle will be also equal to 90 degrees. Likewise, from point Q, we draw the radius QM. Why QM is the radius of the small circle? Because of the fact that Q is the center of the small circle and M is the point on the small circle itself. This is exactly the definition of a radius. So we have the radius QM of the small circle that is drawn to the point of tendency. That is to say, the radius QM is drawn to point M, that is the point of tendency of tangent dB with this small circle, and whenever we have a radius that is drawn to the point of tendency, then the tangent dB will be perpendicular to the radius MQ. So if dB is perpendicular to MQ, it means that that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. So in quadrilateral OQDM, we have 1, 2, 3 right angles. Repeat again. In quadrilateral OQDM, we have 3 right angles. The sum of 3 right angles is 90 times 3 is 270 degrees, plus the size of the fourth angle, that is actually angle OQM. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Here we subtracted 270 degrees from this equation and found out that the missing angle OQM equals to 360 degrees minus 270 degrees, it is equal to 90 degrees. So this angle OQM equals to 90 degrees, it is a right angle. Therefore, quadrilateral OQDM, we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle. So we will relate to quadrilateral OQDM as a rectangle. And we know that the opposite sides of a rectangle are equal to each other. So in rectangle OQDM, OQ must be equal to DM. Okay, OQ must be equal to DM. But we have already found out that OQ is the radius of the small circle, that is to say it is equal to small r, so we can write here that OQ equals to small r. And from this equation, small r equals to OQ equals to DM, we will derive that DM is also equals to small r. Here, DM is also equals to small r. Okay? And what is the length of line segment PM? What is the length of line segment PM? From the drawing, it is very easy to see that PM equals to DM minus DP. Again, PM equals to DM minus DP. Okay, PM equals to DM minus DP. DM equals to R. We have already found out that DM equals to R, that is the radius of the small circle. DP equals to 7/8. We have found out that DP equals to 7/8. So in conclusion, we found out that PM equals to small r plus 7/8. Okay, in the next step here, actually we have point S. We define this point as point S. Point S is the touching point of the small circle with the big circle, and it is also the point of tendency of the two circles. It is also the touching point, and it is also the launch point of those two circles. So point S is defined as the launch point of those two circles, and because of the fact that the small circle is inside the big circle, this point of touching is internal. It is defined as internal launch point or internal launch. Because of the fact that the small circle is inside the big circle, it is defined as internal launch. Okay? And then I presented to you rule number 2. According to rule number 2, if two circles have an internal launch between them, then the straight line that connects their centers passes through the launch point. So here, actually, in this drawing, we have an internal launch between those two circles at point S. And according to rule number 2, we will get that the straight line PQ, actually P is the center of the big circle, Q is the center of the small circle, and PQ is the straight line that connects the two centers together. And according to rule number 2, this straight line must pass through point S, that is the launch point. Again, the straight line PQ that connects the two centers together must pass through the launch point, that is point S. That is to say, points P, Q, and S, they are all located on the same straight line, or line segment PQS is a straight line. Okay, I'll repeat again. Here, according to rule number 2, we get that in our drawing, points P, Q, and S are located on the same straight line, or PQS is a straight line. According to rule number 2, of course. And here, what is the length of line segment QS? Q is the center of the small circle. S is a point on the small circle itself. This is exactly the definition of a radius. So QS is the radius of the small circle that is equal to small r. What is the definition of line segment PS? P is the center of the big circle. S is a point on the big circle itself. This is exactly the definition of a radius. That is to say, PS is the radius of the big circle that is equal to capital R. But we have already found out that capital R equals to 25/8. So in conclusion, we found out that PS equals to capital R that is equal to 25/8 units. And what is the length of line segment PQ? PQ equals to PS minus QS. Again, PQ equals to PS minus QS. PQ equals to PS minus QS. Okay? PS equals to capital R. We have already found out that PS equals to capital R. QS equals to small r. So in conclusion, we found out that PQ equals to capital R minus small r. But we have already found out that capital R equals to 25/8, so we can substitute capital R by 25/8. We did it and we got that PQ equals to 25/8 minus small r. So this line segment PQ equals to 25/8 minus small r. Then I copied the right green triangle in a new page and we implemented the Pythagoras theorem on this right green triangle, triangle QPM. This is the right triangle QPM that I copied from the original drawing. We have already found out that QP or PQ equals to 25/8 minus R, PM equals to small r minus 7/8, and QM equals to R, that is the radius of the small circle. We implemented the Pythagoras theorem on this right triangle. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is PQ, so the square of the hypotenuse is PQ square, and it is equal to the sum of the squares of the perpendiculars. That is to say, it is equal to QM square plus PM square. Okay, so according to equation number 1, QP square equals to QM square plus PM square. QP equals to 25/8 minus R, so QP square will be equal to 25/8 minus R square. QM equals to R, so QM square will be equal to R square. PM equals to R minus 7/8, so PM square will be equal to R minus 7/8 square. Here we open the brackets on both sides of equation number 1. According to the algebraic identity, that A minus B square equals to A square plus B square minus 2 times AB. Here 25/8 minus R square equals to 25/8 square, that is 25 squared, 625/8 squared, that is 64. Plus R square minus 2 times 25/8 times R, and it is equal to R square plus R minus 7/8 square, it is R square plus 7/8 square, that is 7 squared, that is 49/8 squared, that is 64. So in conclusion, 7/8 square equals to 49/64 minus 2 times R times 7/8. So here we have R square on both sides of equation number 1, so R square will get cancelled. So what is left after we cancelled R square from equation number 1? We have here 625/64. Here we have minus 2 times 25/8. We divided both the numerator and the denominator of this. It is actually it is minus 2 times 25R/8. We divided both the numerator and the denominator of this expression by 2. Minus 2 over 2 is minus 1, so 2 will get cancelled. In the numerator, what is left is only 25R. In the denominator, we have 8 that is divided by 2 is 4. So in conclusion, this expression minus 2 times 25r over 8 equals to 25 minus 25r over 4. After we divide it by 2, of course. Here we have r squared plus 49 over 64. And here we have the expression of minus 2r times 7 over 8. We divided both the numerator and the denominator by 2. So minus 2 over 2 is minus 1. So minus 2 will get cancelled. In the numerator we left only with minus 7r. In the denominator we have 8 that is divided by 2 is 4. So in conclusion, this expression minus 2r times 7 over 8, after we divide it by 2, is equal to minus 7r over 4. Here we multiply this equation by 64. And here 625 times 64 over 64 is 625. And here we have 64 minus 64 over 4 is minus 16. So in conclusion, this expression equals to minus 16 times 25r after we multiply it by 64. 64 times r squared is 64r squared. 64 times 49 over 64 equals to 49. And then we have minus 7r over 4 times 64. That's actually minus 64 over 4, that is minus 16 times 7r. Okay? So in conclusion, we got this equation. Uh, 625 minus 16 times 25r is minus 400r. That is equal to 64r squared plus 49 minus 16 times 7r is minus 112r. Here we added 400r to this equation number 1. So we have here 625. 400r minus 400r is 0, so we left only with 625 on this side of equation number 1. And maybe it is equal to 64r squared plus 49. And here we have 400r minus 112r, it is equal to 288r. So in conclusion, we found out that 625 equals to 64r squared plus 49 plus 288r. We subtracted 625 from this equation number 1, and we got here 625 minus 625 is 0, and we have here equals to 64r squared plus 288r, and we have 49 minus 625, it is equal to minus 576. So in conclusion, we found out that according to equation number 1, 64r squared plus 288r minus 576 equals to 0. Here we divided this equation number 1 by 32. So here 64 over 32 is 2. So this expression in total equals to 2r squared. 288r over 32 equals to 9r, and minus 576 over 2 equals to minus 18. And 0 over 32 equals to 0. So in conclusion, we got the quadratic equation that 2r squared plus 9r minus 18 equals to 0. In this quadratic equation, the coefficient a equals to 2, the coefficient b equals to 9, and the coefficient c equals to minus 18. And the variable that we are looking for in this quadratic equation is r, so x equals to r. And the general formula to solve out the quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In this quadratic equation, a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. When we find out the value of x, in this our specific quadratic equation, the variable that we are looking for is r, so here x equals to r. So we substitute x by r. We substitute x by r, we got that r equals to minus b. B equals to 9, so minus b is minus 9, plus minus square root of b squared. B equals to 9, so b squared is 9 squared, it is 81. Minus 4 times a is 2, times c is minus 18. All divided by 2a. A is 2, so 2 times 2 is 4. So r equals to minus 9 plus minus 81 plus minus 4 times 2 is minus 8, and minus 8 times minus 18 is plus 144. So inside the root we left only with 81 plus 144, so r equals to minus 9 plus minus square root of 81 plus 144 over 4. So r equals to minus 9 plus minus 81 plus 144 is 225, so inside the root we left only with 225, all divided by 4. Okay, so here we have r equals to minus 9, and the square root of 225 is 15. So r equals to minus 9 plus 15 over 4. So here we will have two solutions that are possible for r. The first solution for r is that r equals to minus 9 minus 15 over 4. Minus 9 minus 15 is minus 24, and minus 24 over 4 equals to minus 6. So we found out that r, the radius of the small circle, equals to minus 6. That is a negative number, but r, as I already mentioned, is the length of the radius of the small circle. R is the length of the radius of the small circle. So r is a length, it must be a positive number, it can never be equal to minus 6, that is a negative number, so we cancel this solution, and we left only with the second solution, that r equals to minus 9 plus 15 over 4. Minus 9 plus 15 is 6, and 6 over 4 is equal to r. We divided both the numerator and the denominator of 6 over 4 by 2. 6 over 2 is 3, and 4 over 2 is 2. So in conclusion, we found out that r, the radius of this small circle, equals in its length to either 3/2 units, or in terms of numbers, it is equal to 1.5 units. I'll repeat again, r, the length of the radius of the small circle, equals to either 3/2, or in terms of numbers, it is equal to 1.5 units. Okay, thank you very much.